So now we'll have Boes talking about catalytic quantum randomness.
Yes, thanks. So yes, also thanks from me to the organizers for putting up this great event. I'm really enjoying both the awareness part of the of the conference as well as the scientific program. And I need this. So this is joint work with Henrik Wilming, Rodrigo Gallego, and Jens Eisert, all of which were at the Free University of Berlin when completing this research. The title is Catalytic Quantum Randomness, which shouldn't mean anything to you right now, but hopefully it does by the end of this talk. And really the basic idea, the starting point for this research was to compare two ways of using randomness to implement stochastic maps or random processes and compare their relative power. In particular, one that is classical in nature, that thinks of the randomness as classical, and another one that uses sort of quantum degrees of freedom in your randomness. And I'll explain what I mean by that. So let's think about these two models. The first is the following. You have a system, an initial state rho, and your source of randomness is a black box that samples from, say, any distribution, so the uniform distribution from some finite alphabet, and then you sample this, you press a button, you get an I, get an event, and then depending on the I, you implement some unitary on your system, right? And, well, that gives you an output state, that gives you a map. The second way of thinking about how you use randomness is different. There, you still have your system in the state rho, but now your source of randomness isn't a black box. It's itself modeled as a maximally mixed state, right? So this is my notation for a maximally mixed state. And what you now do is instead of pressing a button, waiting for a classical outcome, and then applying a unitary depending on that outcome, you simply evolve the joint system under a global unitary of your choosing, and then trace out the source of randomness. And that again gives you an effective map on the system, right? So more formally, the first of these I'm going to refer to as implicit random channels or random maps. And they're defined by a set of unitaries, M of those. And then the output of the channel is simply given by the equiprobable application of each of these unitaries to your input state. And this is going to be my notation for saying that there exists a set of M unitaries that takes an input state rho to an output state rho prime, yes, in this way. Okay, so contrast this with the second model, which, well, maybe I'm going to change slides. I think this is better. Now, the second model here, you now just have what I had on the last slide. You take your input system, you have the maximally mixed state, you evolve the two under a joint unitary, and then you trace out the randomness. And I'm going to say again that there exists, well, I'm going to write this. If there exists a unitary that takes an m-dimensional maximally mixed state and your input state and implements this channel such that the output state is given by rho prime. So I'm going to be interested in the state transitions you could implement in this way, right? And the basic question is, how do these two models differ, right? How might they differ? They might differ in the kinds of transitions you could implement, or for example, in this M, right? So before I go into this, let's ask for some motivation. Why study this? There is a bunch of those motivations I could give you. One is that a lot of key information theoretic quantities have been characterized operationally at some point by asking this kind of question, by asking what's the least amount of randomness, or what's the smallest maximally mixed state that I need to add to my system that I later need to trace out in order to implement a certain protocol, a certain task. And then what these authors did, and I think there is others as well, is to show that in order the answer to their question, what's the least amount of randomness required to implement a certain task, that gives exactly certain quantities. So the mutual information, the max relative entropy, and so on, right? So understanding better what's the least amount of randomness required to implement a certain task would help us maybe improve on the tightness of these operational characterizations. Another motivation is just more generic, understand the difference between randomness in the classical and the quantum context. So, these two things seem to be entirely different beasts. We have a lot of difficulty producing, genuine randomness, or, good pseudo-random numbers when everything is deterministic. In a quantum context, it seems like if I have access to measurement and I can prepare Bell states or plus states, then generating genuine randomness is the easiest thing in the world. But I mean, so understanding the difference between these two models might help us understand the difference between randoms in a classical and a quantum context. And we've already seen that there are differences. For example, Ralph's talk about the clocks, we saw an advantage in using those. There are others where people use so-called quoins to use superposition states to prepare bias functions, kind of simulate certain coin throws, biased coin throws, in a way quantumly that you couldn't do classically. And the third motivation I'm going to give you is that this explicit randomness, the second model, is a kind of toy model for quantum thermodynamics, where now the maximally mixed state is simply sort of the bath, the degenerate Hamiltonian bath that your system is interacting with under a global evolution that is generated by the joint Hamiltonian, for example. Okay, so now back to the question, how do these two models differ, if at all? One first partial answer is that they don't differ in terms of the reachable state sets, in terms of the state transitions that you could implement if you have access to unbounded randomness, right? So this is the statement here, and we think we should know the notation by now. So this says that any state transition that is possible in using a random unitary channel, if I give myself access to sets of unitaries of any size, I could also implement with a quantum channel. Well, this direction is obvious, but the other way, it's also true, right? I don't get an advantage by taking into account the degrees of freedom of my source of randomness, the quantum degrees of freedom, if I allow myself access to any kind of randomness. So there's no difference in that sense. So an obvious thing to ask then, well, maybe there's a difference if I consider the least amount of randomness that I need to implement a given state transition. So what I could define to answer this question is the following quantity takes as its input the input and the output state, and I say what's the smallest m such that this transition is possible with m, where x could now be a capital C or a capital Q, right? And these two, m star C and m star Q might differ. However, it turns out that this question seems to be aimed a bit high, because already the kind of classical version of this problem, where I replace my density matrices by probability vectors and my unitaries by permutations, seems to be, turns out to be NP complete. So in general, it's very difficult to answer this question, what is the least amount of randomness required? So let's aim a little bit lower, and let's ask a different question, which is, what's the least amount of randomness required to implement any transition that is possible in a given and fixed dimension, right? So I'm going to modify my definition of this quantity here to be now a function only of the dimension of the Hilbert space that my systems act on. I'm going to ask what's the smallest m, value of m, such that if a transition is possible using any amount of randomness, it is actually possible using at most, m amount of randomness, where m is now the number of unitaries, remember, in the classical case, or the dimension of the maximum mixed state in the quantum case. And if we've defined these two quantities, you get simple entropic lower bounds. So it's easy to see from entropic considerations what are the best possible values that these two quantities could take, and already we see a difference. So in the classical case, we find that this m star C of D will have to be at least as big as D. And in the quantum case, we find that actually the lower bound is lower, strictly lower. It only sits at the square root of D, right? And last year there was a paper where this bound was shown to be tight, right? So there exist implicit, like random unitary channels, implicit constructions that allow you to implement any transition that is possible using any amount of noise, using exactly d many unitaries in this implicit way. And basically the technical main result of this project is that we show the second inequality also to be tight, right? So anything you could do with noisy operations, with these with this explicit way of using a randomness, you could actually do with a bath, well, with a source of randomness, the maximum mixed state, whose dimension is only the square root of the system, the dimension of your system, or in sort of logarithmic units in terms of numbers of qubits that you count, half as many qubits of maximally mixed states suffice to implement any transition that is possible. Now, this is interesting for a number of reasons. For example, knowing the second bound to be tight establishes a strict separation between the power of these two ways of doing it, right? I mean, sort of up to here it was possible that this wasn't tight, but this was tight. Now we know it isn't the case. And so taking into account the quantum degrees of freedom of your source of randomness does always allow you, like in any non-trivial dimension, to have a strict advantage. All right, so the rest of the talk is going to be about proving this quickly, and then talking about some applications of this. But before I do that, I want to give you kind of a feeling for just why this particular square root d bound is also kind of interesting or surprising. Because, I mean, what really is going on here is that let me just give you an example, because otherwise I'll stumble across some weird formulation. All right, so here's one thing that is fairly easy to see. Both classically and quantumly, right, both under a classical and a quantum setting, this transition is possible. You take a 2-qubit pure state, and you want to map it to a 2-qubit maximally mixed state, right? Now, this is easy if you have unbounded randomness, because you just take that randomness and you swap it, or you twirl over your system, right? So this is possible if I give you any amount of randomness. But the result tells me that I should be able to do this with just a single qubit of noise, right? In a quantum way, right? So let's think about what this means. This means I have my single qubit in a maximally mixed state. I have my two pure qubits. And now this result tells me that there exists some unitary that I apply to the 3 qubits, and then afterwards this will leave me in a system that has locally the marginal states of these 2 qubits will now be maximally mixed each. And this is in some other state, and they might have established correlations along the way, which is not something I'm caring about right now. But of course, I could just cascade this, right? I could now use these 2 as new sources of randomness to implement the same transition on a new set of pure qubits, and so on. Right? And this is obviously something I couldn't have done classically, because classically, the lower bound I gave you was that the dimension of the noise had to be at least the dimension of the system. So I couldn't have had this sort of cascading, this growing, where I get an exponential number of locally sort of marginally uncorrelated maximally mixed states at the leaf nodes from starting just with a single maximally mixed qubit at the root, right? Anyway, so let's talk a bit about applications and the construction, and finally also about the catalyticity. I think I'm okay with time. So the construction is very simple. So by construction I now mean, how do we prove the tightness of this quantum bound, this lower bound? And the construction rests on this simple insight, which is that let's it's not really important, but let's add a Q here just to have the notation clear. So the following is true. If I can do a transition with any amount of randomness, then there exists a unitary channel, which just conjugates the system by unitary, and a so-called dephasing map, such that this transition is implemented by first applying the dephasing map and this unitary channel. And what is this dephasing map? It just fixes a basis on the system, an orthonormal basis, and then the effect of this map is that it maps all the diagonal entries of the density matrix in this basis to itself, and all the off-diagonal elements to 0, right? So it dephases the system in that basis, right? So if you could do it with any amount of noise, you could just dephase it in a given basis. There exists a basis A and a unitary channel U such that this right-hand side is fulfilled, right? And so since we're interested in asking for the least amount of quantum randomness that allows us to implement any transition that is possible, we can now, ask instead, what's the smallest amount of randomness, what's the least amount of randomness required to implement a dephasing channel? Because the unitary channel itself doesn't require randomness, it's just a unitary on the system. And so this is the key lemma. For any basis A, you can realize this dephasing lemma as an explicit random quantum channel where the amount of randomness you need is just the square root of the dimension, right? So it's conceptually very clear. We first implement this dephasing channel using a source of randomness whose dimension is the square root of the system dimension, and then we apply a unitary channel to implement any transition that's possible. And proving this key lemma is also a two-line proof. I mean, we have it in the main text, I think, of the paper. You just choose a unitary operator basis on the source of randomness, right? Not on the system, on the source of randomness. So an operator basis that where all the v's are unitaries and they additionally satisfy this condition on the Hilbert-Schmidt product. And now you define this unitary, which is essentially conditioning on the state of the system and then applying one of these elements of the unitary operator basis to your randomness, right? And then you just evaluate this, and in 2 lines you find out that this key lemma follows, and then from what I told you about on the last slide, the rest falls in place. And the kind of conceptual novelty here is, I mean, it's very simple now that you think about it, but the point is that when you used your randomness classically, what you always did was to condition on the state of the randomness, that is the value it's spit out, and then apply some non-trivial operation, some unitary, to your system. Now what we just do is we condition on the state of the system to apply a non-trivial operation on the source of randomness. And of course we could only do that if we model our source of randomness as a quantum system, right? I mean, you couldn't do that to a black box. Okay, so that's the construction, it's very simple. Let's talk about some applications. First, there's a bit of a sort of gadget-like application, which is once you have this thing, you could think about the smallest possible decohering environment that is compatible with quantum mechanics. In the following sense. You have your system, an initial pure state psi, you have an environment in a pure state phi, and what I mean for something to be a decohering environment, I mean the following: for this environment, there exists a unitary U such that the local effect on the system in the initial state psi is to dephase the system in an einselected basis A, right, in the einselection basis. And now we ask, well, what's the smallest possible decohering environment? What's the smallest dimension of E such that there exists an initial state phi, like an initial pure state phi, and a U such that this is satisfied. And what we do is very simple. You just pick a kind of bipartite environment, E1, E2, and you initialize this environment in a maximally entangled state over these 2 subsystems of E. And now, of course, each of these is locally in a maximally mixed state, right? So we use half of the environment, E1, say, as our source of randomness. We apply a dephasing construction, and we're done, right? So we can decohere a system in any basis using an environment that has the same dimension as the system itself. Of course, I mean, I'm not suggesting that this is how decoherence occurs, and this is the physical mechanism. This U is highly non-local, and so on, right? So we're ignoring kind of the real physics going on here, but the point is more that you see that already a tiny system, I mean a tiny environment, an environment of the size, the same size as the system, is sufficient to induce dynamics that decohere the system, right? So it's sort of extremely fragile to decoherence. And sort of using a similar reasoning, we can also talk about the smallest possible measurement device, where now the environment is replaced by something that has a pointer and a reference and so on. I'm not going to talk about this. And here's another application, a private quantum channel. So what's a private quantum channel? Well, let's think of the following situation. you have Hannah Arendt, the political writer and philosopher, sitting in the 20th century and wanting to communicate with Hildegard von Bingen, the 11th century polymath. So they want to exchange messages, ideally quantum data, this psi here. However, there's a problem. There's Nicholas, I forgot the name already, Eimerick, with an E, it starts with an E, who's one of the big inquisitors, 15th century, right? One of the early witch hunters. So he should definitely not get his hands on what Hannah and Hildegard have to say to each other, right? So what are they going to do? Well, ideally, they're going to find a private quantum channel. So Hannah encrypts psi using some mechanism, and then this encoded state passes by Nicholas Eimerick, and then Hildegard then, what's it called? Decodes the thing using another fixed mechanism. And such a scheme is secure. I mean, this is sort of kind of hand-wavy. If the mutual information between the encoded state and the original message is negligible, or even zero exactly, and it's reliable if in your distance measure of merit, the distance between the decoded state and the initial pure state psi, the initial message, is also negligible. So if Hannah and Hildegard have access to a one-time pad or like a classical key, then what they could do is that they start off with this. I mean, this is now the qubit here that sits in this psi, and then Hannah Arendt could use a 2-bit one-time pad to say, well, depending on the value of the first bit, I'm gonna implement a Pauli Z on this qubit, and depending on the value of the second, I'm gonna apply a Pauli X or not on this qubit, right? And so she does that. She sends it off to Hildegard, sitting in the 11th century. But when Nick sees it passing by in 15th century, he's like, well, I don't know which of the 4 possible combinations of Pauli X and Z they did. So for me, this is a kind of like a twirling map that they implemented. Any initial state psi, not only pure states, would have been mapped to the maximum mixed state because it's a randomizing channel. So the mutual information between the state that E sees and the one that A encrypted is by construction 0. Hildegard can just undo the operation on her end, so she gets the exact same state back. It's a perfectly reliable channel. So this is a standard construction, and you note that locally A and B use their randomness in a classical way, right? They condition on the state of the one-time pad and they apply it. What else could they do? I mean, it's a one-time pad, it's a classical string, right? So what if we replace the classical key by a quantum key, right? So Hannah and Hildegard rock, so they have entanglement. And now we move to the setting of an entanglement-assisted private quantum channel, right? And this has been studied by Debbie Leong in 2002 already, who uses the same local encryption and decryption mechanism. And she has a discussion of a bunch of properties that now, where now you get advantages, such as reusing entanglement, key recycling, and so on. However, she doesn't alter the way A and B locally use this randomness. So using these constructions that we have, okay, I should actually hurry up. We have that I've presented to you, you'd actually modify these a bit, like if you use them in a clever way, to halven the amount of entanglement needed to get exactly the same effect. So have the same security and the same reliability. And this is provably optimal, with respect to the diamond norm. Also, if you have approximate channels, not just the perfect channel. All this is in the paper. So that's an application of this. If Nicholas doesn't do anything, if E doesn't do anything, then the entanglement is at the end not used up. You can do error correction by measuring your E bits, and you can do key recycling, although I should say that most of these things we just took over from Debbie Leong's construction, right? So they're not something we had to work very hard on. Okay, so finally, I haven't said anything about catalyticity. what do I mean by this? Well, here's a fact. You use this UQ that I defined earlier, which is this dephasing unitary. You apply it to any state, and it so happens that if you looked on the effect on the source of randomness, so you trace out the system, actually, it remains in a maximum mixed state. So locally, it hasn't been changed, it hasn't been altered. It wouldn't have had to be this way, but it turns out to have been like this. So what we get here is an interesting trade-off, right? So using this, you could just, taking this into account, you could just reuse the same source of randomness again for multiple iterations of this procedure, right? And what you will end up with, you have lots of rows coming in, you have your initial maximum mixed state, and now you use the same to implement the dephasing map on all of them, or implement the protocol of your choice to all of them. However, this now comes at the cost of correlating all the systems between each other, potentially, because you initially correlated the system with each of those, right? So, okay, and this is in contrast to a set scenario where you use a new source of randomness for each new iteration, and there you only have correlations. So locally these copies end up uncorrelated. However, at the cost of using more randomness. So there's this trade-off, which is nicely illustrated. And when we realized this, Hendrik and Rodrigo and Jens and I were so excited about this that we wrote a whole new paper about it. And we said, oh, this is great. And we generalized this. The setting we considered, and I quickly want to advertise this, is the one where now the ancilla, the randomness, is not anymore in a maximum mixed state necessarily. It could be any state. And we ask, what are the possible state transitions, row to row prime, that I could implement or approximate arbitrarily well using a possibly fine-tuned catalyst sigma, such that locally the state remains unchanged. However, you can establish correlations. And we have a conjecture in the paper where we say that this is exactly characterized by the increase of the phenomenon entropy, right? So this is interesting for a number of reasons that I can't go into. I invite you all to work hard on this, because we did for many months and we couldn't find a solution. But it would be, I think, very interesting for it to be true or known for it to be false. Okay, so also in the paper, we have robustness of the protocol that I didn't talk about. So both of the maximum mixed state isn't actually maximal, it's kind of something else. We could still implement these dephasing channels approximately. Also, there's robustness in the time implementation of this whole thing. So if your unitary that implements the dephasing channel isn't well timed, you could also, kind of get the program doesn't the map doesn't crumble. It's robust against these things. We have bounds for the approximate dephasing and randomizing channels, and as a very odd feature, we also have an expander graph construction that doesn't fit with the rest of the paper, but is, I think, interesting for people interested in expander graphs, where we show convergence in 2 norm that is exponential, whatever. So outlook, what can we do? We can basically take this conceptual twist. We now use randomness in a quantum way to pretty much anywhere that people use randomness classically. So we could ask, well, do we get an advantage by now thinking about the randomness quantumly? There is a promising application to tensor networks, and in particular these mirrors, which is related to this cascading of noise that I showed on some slide. We have these hardness results about the classical case, the NP completeness of deciding sort of the exact amount of noise, the minimum, so that's something that could be worked on. There was an idea to use this for sort of multipartite schemes to have this private quantum channel in a multipartite scheme. We didn't have anything good enough to include in the paper. And with this, I'd like to thank you.
So we have time for 1 or 2 quick questions. Anyone?
So what's the unitary that you use to generate 2 classical uncorrelated random bits with 1 identity state as the ancilla?
Sorry, can you repeat the question for the quantum channel? Or
Well, so in that big cascade, you generate 2 random states using 1 as a resource. What is the unitary that does that?
Yeah, the unitary I had, it's this one. So you take right, so now you have, this is now the system in the maximum mixed state, and this is the 2-qubit system S. And now you take any unitary operator basis on the system, right? And the number of elements in a unitary operator basis is the square of the dimension of the space it acts on. So you have, say, if this was a two-dimensional system, you have 4 of these, for example, the 4 Paulis, with the identity. And then you have 4 projectors. They have d many projectors onto the system, the 2-qubit system. So it's a super simple construction, and it does all the magic.
Questions?
Thank you for the nice talk. I have 2 quick questions. First, I understand the motivation coming from Thermo that you take maximally mixed state, but what if you take any classical state on this ancilla, and how results would change? And another comment is those bases of unitaries, they are related to interpretation schemes. Right, there was a paper by Werner of this. Is there some deeper connection to interpretation here hidden somewhere?
Okay, so I mean the answer to the second question is yes. However, it's not. I mean, there was a long time where we thought, we could use this to come up with an improved superdense coding scheme, and then we realized that this was somehow just teleportation, superdense coding already in disguise. So if you, I mean, the point here is that we get this advantage, we get this factor of 2 by entangling the source of randomness with our system. And if you were thinking about these cryptographic applications or like having kind of communication protocols between parties, then you realize that when you send things over, you kind of do 2 steps of a superdense coding protocol where you use up your entanglement and then replenish it in kind of 1 step. So there is a connection. It's sort of slightly too complicated to just tell you now, but yes, that was the right intuition. With respect to the first question, well, as I said, there's robustness of the protocol. So if your aim is to use the source of randomness as a source of randomness, but you cannot certify that your state is close to actually being maximally mixed, then it still works. You could sort of distill the randomness. And in fact, there's an interesting thing where if you have a source of just 1 state, right, you don't have any randomness, you have just 1 state, and this state has 1 norm distance from the maximum mixed state less than 1, right? Then, or sort of trace distance less than half. Then you could use this, you could use many copies of this state to distill the randomness that you need to dephase a single copy of this in any basis you like. So there are things that you could do with, I mean, I don't know, maybe sort of sufficiently classical states, or at least states close enough to the mixed state, but without having any randomness. This is also in the paper in some detail.
So let's thank the speaker again.